Hey everybody, thanks for tuning into this talk that I've very blandly titled Toward a More Secure IP Camera. I know that a lot of these talks tend to focus on breaking into things, but I thought I'd change things up a little bit by talking about a project in which we actually tried to increase the security of an IP camera, and in particular the data stream coming off of it. My name is John Tyner, and I'm the principal software engineer at Ubix Security in San Diego, California. We're mainly focused on delivering a quote-unquote encryption as a service platform, making encryption stupid simple for developers. But a portion of our business still involves application-level data encryption on desktop and embedded devices, and that's what this talk is going to be about today. Alright, so we'll sort of jump right into it here. We were approached by a customer who was looking to implement a camera security system in which the data is encrypted at the end device or on the camera, and delivered to a video management system, which I'll just refer to as a VMS from here on, and stored without having to be decrypted and re-encrypted at the VMS. Most systems, if they use SSL, they pull the data onto the camera, but the SSL connection is terminated, the data gets unencrypted, and then if it wants to be stored, it has to be re-encrypted. We were trying to avoid that. I should back up here and explain that Ubix Business started out building an encryption library that takes large data objects, fragments them into smaller pieces, and then separately encrypts those pieces and stores them to a variety of media. As you can imagine, the separate encryption lends itself to computers with multiple cores since the encryption is highly parallelizable at that point. The process also benefits from being able to write the encrypted fragments to multiple locations simultaneously from different threads. As it turns out, this scheme also works well over the network since we can tune the fragments to be sizes that are easily transmissible over various network links. Back to the use case here. The other requirement here in the second bullet point is that the customer wanted to use Axis cameras for this system. This worked well since Axis provides what they call the Axis Camera Application Platform. The Axis camera is basically running Linux, and Axis via this platform allows third parties to embed software into the camera and use the platform to hook into the camera hardware. The current state of most cameras is to provide an audio and video stream via RTSP. It's a widely adopted standard for streaming video, and every free VMS that I've played with has support for it. RTSPS was out for our project, as I mentioned previously, as the customer desired to avoid SSL. We also looked at trying to intercept the RTSP stream coming off of the camera, but one, the protocol is actually broken into separate control and data streams. Two, the protocol is complicated for what we wanted to do, which is simply receive, store, and possibly simultaneously play back the live received stream. And three, we didn't want to be in the business of parsing out the RTSP. We also looked at trying to encrypt the native Axis stream, but Axis transmits the stream over in the existing HTTPS interface, which would require too much effort to detangle the control and data without breaking just about everything. So in the end, we were left with trying to roll our own scheme for transmitting the stream off of the camera. Step one was to establish some level of trust between the client and the camera or server. Because we didn't want to be administering passwords on every different camera in the customer's infrastructure, we opted to set up a basic public key infrastructure or PKI. For simplicity's sake, in the initial implementation, the camera verifies that the client is allowed to connect. The data only flows one way, from the camera to the client, and therefore it was more important that the client be verified. As I mentioned on the previous slide, RTSP is actually two separate connections, usually one TCP and one UDP. For our purposes, we only use a single UDP link. Because there's no connection phase as in TCP, the client has to send a hello message to the camera. This message contains a public key that has been assigned to the client and signed by the Customer Certificate Authority, or CA. The client then signs this message with his private key and sends it to the camera. The camera, when it receives this message, verifies that the certificate has been signed by the CA. This verifies that the client certificate is trusted. The camera also verifies that the message has been signed by the private key associated with the certificate's public key. This proves that the sender of the message is the owner of the certificate in question. If either of those checks fails, then the message is silently discarded. If the checks succeed, then the camera hooks into the video stream and begins to deliver that stream to the client. Before the stream is delivered, the camera sends what Ubix calls a manifest. This manifest contains a fragment location base variable. This variable is unique to each manifest and can be used to randomize fragment storage locations. I'm going to skip any further explanation of this for the time being. We'll come back to it later. More importantly, though, the manifest contains the fragment key base. This is another value that is unique to each manifest. This value is used to derive the keys for all fragments associated with the manifest, and in particular, access to this value would allow the holder of it to decrypt all associated fragments. The manifest can also contain other metadata and information about where to store the fragments, but again, I'm going to skip any deep discussion of those fields. The manifest is encrypted using AES 256, and this is shown by the lower blue shaded portion in the graphic on the slide. The AES key is then encrypted using the client's public key, which was received in the client's hello message, and this is shown by the red shaded portion. Now the real fun begins. With the manifest out of the way, we tap into the camera's frame grabbing interface and begin receiving video frames from the camera hardware. Depending on the camera settings and the amount of motion in the frame, each frame can be anywhere from kilobytes to megabytes in size. If you recall, we want to tune the fragments encrypted under the manifest such that every packet sent is a separate encryption. This means that we need to break each frame down into fragments that are less than the MTU size of the network link. Each packet sent over the network contains 4 identifiers in addition to the frame data. The first is the epoch number. This number indicates which manifest the fragment belongs to. This value is sent in the clear. The second identifier is the fragment number. This number is also sent in the clear and indicates which key was used to encrypt the fragment. Remember from the previous slide that the fragment encryption keys are derived from a unique value kept in the associated manifest. The third identifier is the frame number. This identifier is simply a number that identifies the frame number as it comes out of the camera hardware and is used for sequencing. This number is encrypted. The final identifier is a sequence number. This number identifies a fragment within a frame. It tells the client in what order to reassemble the frame, and this number is also encrypted. Finally, the encrypted data follows. Hopefully this diagram makes it a bit easier to follow all of that. You see at the top the epoch and fragment number in the clear, followed by the frame and sequence numbers and the frame data, all of which are encrypted. Below that, I've tried to lay out how these numbers work in practice. Here's an example of 10 packets that make up 4 frames of camera data. You can see the first grouping of 3 packets represents the first frame from the camera. That frame required 3 fragments. The second grouping of 2 packets represents the second frame. Note that because the frame number is encrypted, it's not possible for an external observer to tell, absent any other information, how many frames were transmitted in those 5 packets. The third and fourth frames were encrypted under a new manifest. You can see that because the manifest changed, that caused the fragment counter to reset. However, the frame counter continues on independent of those other values, and the sequence counter resets for every frame. That sort of covers the meat and potatoes of the protocol. It's really meant to be a very simple means of sending data extracted from the camera encrypted to the client without a lot of bells and whistles. The message formats are fixed, and there's not really any negotiation possible as far as crypto algorithms or message authentication as there is with SSL. That said, there are some other considerations that arise as part of the protocol. First is that the client can resend its hello message at any time, which will trigger the camera to resend the current manifest. The client will obviously need to do this whenever a fragment with an unrecognized epoch is received, but the client has to do this on a regular interval anyway as a keep alive for the connection. Because the connection is UDP, the client has to keep telling the camera that it is still present and wanting to receive the data stream. Conversely, the client stops the stream by halting the sending of the hello messages. The camera is in control of the manifest epoch and can and will change it for one of 2 reasons. The first reason is that the epoch has to be changed in order to reset the fragment counter. Note that the epoch counter is allowed to wrap around on the assumption that by the time the epoch number is reused, it will have been so long since the last time that the number was used that there can be no confusion. The other reason for changing the epoch number is for changing the manifest. Changing the manifest enables forward secrecy by changing the base key from which fragment keys are derived. Finally, the encrypted frame packet may contain other data. In our case, our project was a proof of concept in which we terminated the encryption before reaching a VMS system. Integration with a VMS is for another phase of the project. Because of that, we included a presentation time value from the camera that is used for decoding the stream in GStreamer. So what does the client do with this data? Well, obviously it can decrypt it and play it back. Remember from our initial use case, though, that the goal is to be able to store the data as received from the camera. The most obvious method of storage would simply be to store the manifest by their epoch numbers and the fragments by their epoch and fragment numbers. Using those identifiers to name the files, the data can actually be stored exactly as received from the network and played back later, so we achieved our initial goal there. Of course, fancier schemes are possible. The manifests themselves are very small. As I mentioned earlier, the manifest can contain other metadata, and the client could add metadata to the decrypted manifest and re-encrypt it prior to storage without any real hit to performance. Furthermore, since we're talking about video streaming, the manifest could be named to include timestamps indicating when they were received, and this would enable easier seeking during later playback. As always, there's plenty of work left to do on this protocol. The main focus for improving it is the authentication of the connection. As described earlier, there's currently no mechanism in place for the client to establish that the camera can be trusted. As such, it would be trivial to impersonate a camera on the network. There's also currently no authentication of data frames received from the camera. Even though the frames are encrypted using AES-256 in GCM mode, the plaintext portions of the packet are not covered using the additional data mechanism of GCM. They could be, but if we went this route, it would introduce a related problem. When the epoch changes, the client cannot decrypt or verify the message because it has not yet received the new manifest. By crafting a bogus fragment message with a new epoch, an attacker could induce the client to erroneously send a hello message, and depending on the client implementation, possibly lose sync with the camera. Related to sending the hello message, some sort of replay protection is necessary for that message. The message, as it is today, is basically a fixed format and can be replayed at any time without having to recalculate a new signature for that message. Finally, multicast is another feature that can be added to reduce the load on the camera device. Currently, each new client is treated separately by the camera. Therefore, the camera would have to encrypt each frame separately for each connected client. However, there's no reason that the current manifest couldn't be separately encrypted for each client, with each manifest containing the same unique values. This would allow the manifest to be different per client, while allowing all clients to decrypt the same fragments. The fragments could be duplicated to each client, or they could be sent to a multicast address to save on network bandwidth. Way back on slide 5, I sort of glossed over the fragment base location field in the manifest. As I mentioned even further back on slide 2, the fragment encryption scheme I described is part of an encryption library that Ubik developed several years ago that has the capability to spread fragments across multiple media locations using indecipherable file names. While not security critical, there are some cool things that can be done that would help prevent someone who came across stored fragments from understanding what they were looking at or how the fragments fit together into a larger whole. Let me explain. Using the metadata fields in the manifest I mentioned earlier, the client can store the paths to multiple storage locations, say several S3 buckets. Then using the fragment base location in the manifest, which is unique per manifest, the client can choose one of those locations and a random file name at which to store the fragments. If you look at the diagram, you can see that someone stumbling across one of those buckets would have no idea what they were looking at. The file names don't give away anything about the contents of the file, and adjacent fragments aren't stored anywhere near each other. Only someone with access to the manifest would be able to reconstitute the fragments into their proper order and decrypt them. And with that, I'm going to wrap this up and return you to your regularly scheduled program of interesting talks. I hope this was a useful view into trying to secure an IP camera and that I didn't leave too many gaping holes to get in through. As this is my first talk at one of these kinds of events, I'd like to thank ISE for giving me the opportunity to speak. And if you have any feedback or questions, please hit me up on the IoT Village Discord at jtyner or by email at jtyner@ubicsecurity.com. Thanks again.